Hello students, welcome to 60 out of 60 in KCET Chemistry 2025 series in just 200 days. So yes, now as you all know, we have started a series where we are going to cover every concept that is going to be asked in your KCET examination, as well as we are going to practice a lot of MCQs and previous year questions. So today in this video, we are doing haloalkanes and haloarenes chemical reactions. Okay, so this is very important topic. So we are going to discuss a lot of reactions that these haloalkanes and haloarenes undergo, and apart from this we are also going to solve today a lot of questions. Okay, so yes, if you are an aspirant of KCET 2025, then I request all of you to sit with a notebook and a pen and then note down all the important reactions, all the important questions, and practice with me. Okay, so yes, I hope all are ready for the today's class. Let's get started now. Before that, one more request, please join our WhatsApp channel. The link of the WhatsApp channel will be there in the description section. Okay, so it is important to join the WhatsApp channel to get the notes PDF format of these notes and to get question papers, solutions. As you know, we are conducting weekly test series also. So for everything you need this WhatsApp channel. Okay, so please do not forget to join the WhatsApp channel. Okay, so yes, now I hope all are ready. Please now full focus on today's class. This is very important. Let's start now. Okay, so first of all, if I discuss how are we going to cover this chapter, so this I have discussed almost in every video. So this I am doing every time so that you can also do revision accordingly. So in part 1 we have already covered classification and nomenclature and the structure of CX bond. Then in part 2 we have already covered preparation of haloalkanes and preparation of haloarenes and physical properties. Now in part 3 we are going to cover chemical reactions. Okay, and in part 4 we are going to cover polyhalogen compounds. So this is one of the most important topic, that is chemical reactions. Okay, so now coming to the year wise weightage. So every year you can at least expect 3 to it is varying somewhere 4 questions, 1 question, 3 question, even 0 question. So you can expect 2 to 3 questions from this chapter. But yes, this chapter is very important because it is the basic for the other organic chapters also. Okay, so now reactions that you are studying here will be used in the other organic chapters. So it is very important to master this topic. Clear? Okay, now coming to the today's thing that we are going to discuss chemical reactions. So we are going to discuss chemical reactions of haloalkanes and haloarenes. Okay, now in haloalkanes what we have? Nucleophilic reactions, then we have elimination reactions, and then we have reactions with metal. Okay, so please make this flow chart. It is very important. Now when you are revising, you should have this flow chart and you should remember, okay, nucleophilic reactions, what all reactions were there. In elimination reactions, what all reactions were there. In reactions with metal. So these headings should be very clear. Okay, so now coming to haloarenes. So nucleophilic reactions, haloarenes, and electrophilic reactions we are going to study, and then reactions with metals. Okay, so let us revise it once again. We are going to study the chemical reactions of haloalkanes and haloarenes. In haloalkanes we are going to do nucleophilic reactions, elimination reactions, and reaction with metal. In haloarenes also we are going to do nucleophilic, here elimination, here it is electrophilic, and then both are having again reactions with metal. Okay, so now let's get started here. Okay, so now we are first topic is haloalkanes. Haloalkanes chemical reactions. So under nucleophilic reactions we are going to discuss what are the different nucleophiles and what are the type of nucleophilic reactions. Getting? So again I'll revise. Haloalkanes we have studied 3 reactions: nucleophilic, elimination, reactions with metal. Now in nucleophilic we have segregated this topic into 2 parts, that is different nucleophiles and types. Okay, now coming to here, different nucleophiles. So I'll just explain what happens here. See, this is haloalkanes Rx, and in the nature of bonds we have discussed, this is delta minus and this is delta plus. Now here what happens? A nucleophile attacks, right? Nucleophile will attack in the most electropositive center, so I'll get RNU. Okay, so this is the basic mechanism of any nucleophilic reaction here. Now what happens? We have to see what are the different nucleophiles available and what are the products formed with there. Now you can see here that if I take NaOH or KOH, okay, NaOH or KOH, the nucleophile produced here will be OH. So in place of this NU, you have to add this OH. So if I add OH, I'll get ROH, and that will be one alcohol. Now similarly, if you take H2O, okay, that will also, the nucleophile itself is H2O, and here also the product is ROH, and it is an alcohol. Now if you have NaOR, okay, if you take NaOR, then here the nucleophile is RO minus. Now this RO minus you have to replace with this nucleophile. So what I'll get? I will get here RO R dash, right? So RO minus attacks like this, and this nucleophile goes out, okay? So now we'll get ROR, so that is again a ether compound is formed. Functional group is ether. Now if you want NaI, if you take I minus will get attack and will get Ri. If you take NH3, NH3 is the nucleophile, and it will form RNH2, that is primary amines, okay? Now coming to R dash NH2, here R dash NH2 if you add, we will get RNH R dash, and this is a secondary amine. If you have RNH and then that is the nucleophile, we'll get tertiary amines here. Now this is important, KCN and AgCN. If you take KCN, CN minus is the nucleophile, and we will get RCN, and that will give you cyanide of, go.
Switch off.
Before this you only came.
No, Arun came.
For what?
Pata nahi. Will you switch off?
Haan.
I am leaving.
Haan.
Huh? Pakka.
Haan.
Sure.
What all switches I have to switch
Everything.
off? All switches only I have to switch off, right?
Haan.
Okay.
Pakka.
Sure.
Sure.
Pakka.
Off the AC.
Haan. Okay. Okay. Next, if you have AgCN and you take AgCN, then here the nucleophile is your NC, okay? So now what happens? So this one is, sorry, it is like this, NC, okay? So now we get isonitrile as the product. Now if you have NO2, okay, K plus and NO2 minus, so NO2 minus will attack on the R, and we get RONO, and this is called alkyl nitrite, okay? So now if you take AgNO2, then we will get ONO, okay? RNO2 will be attached, and this is called nitroalkane. So remember here, for KCN, CN is attached, for AgCN, NC is attached, but for KNO2, ONO is attached, and for AgNO2, NO2 is attached, okay? Next, coming to RCOOAg, so here the nucleophile is RCO minus, we will get RCOR, this is an ester. And if you take LiAlH4, we will get H minus, and RH, that is a hydrocarbon. If you take any R dash M plus, so R minus will attack R dash, that is your alkyls. So what is this M plus? M plus stands for any metal. Okay, so this is very simple, you just need to remember which all are important. I am telling you, this all are important, which I have put cross mark, okay, or I'll put like this, so that these are important nucleophiles that you must remember, okay. LiAlH4 also important, okay. Next, coming to types. So in this we have, so there are two types of nucleophilic reaction. One is SN1 and another is SN2. Okay, so now what is the meaning of SN1? First I will explain. See, suppose this is your new Rx. Okay, now when SN1 happens, there is step 1. What happens, we'll discuss it very briefly, because we are going more towards competitive nature. Okay, how is it to solve in competition? So X minus goes here and we form R plus. Okay, this is step 1. In the second step, what happens, this R plus is attacked by the nucleophile to get RNU. Clear? So this is your SN1 mechanism. Now in SN2 what happens? SN2 what happens? Rx is there and then Nu is there. Okay. Now this Nu will attack from the opposite side and will get NUR. And before that, one intermediate is formed, or a transition state is formed. We call it Nu, R and X. This is a transition state, okay, and this is an intermediate. What is this intermediate? Carbocation intermediate is formed, okay. So now if you see the differences between them are very important. So this is a unimolecular reaction, means in SN1 what happens, only one. So this is the slowest step. The first step is the slowest step, right? So the rate will depend only on Rx. So this is a unimolecular reaction. Next, coming to in this one, it is a bimolecular reaction, means it depends both on the concentration of Rx also and concentration of Nu also. So if I want to write the rate law here, R will be equal to K into Rx, okay, and if I want to write rate law here, it will be R into K into Rx into Nu. Okay, so now in this way we can get that this is a, you can say this is unimolecular and this is bimolecular reactions. Okay, next the second step here, it follows first order kinetics. So you can see here the order will be 1 and here the order will be 2. It follows second order kinetics. Okay, now mechanism of SN1 involves 2 steps. So the first step is formation of carbocation and the second step is attack of nucleophile. And here what happens, SN2 reaction involves a single step. So there is a transition state formed and from this transition state the product is obtained. Okay. Next one, rate of the reaction depends on the concentration of substrate only. So rate is depending only on Rx. You can see here. Here the rate depends on the substrate and the nucleophile. So that also you can see from the rate law that rate depends both on the Rx and the nucleophile. Next, carbocation is formed as an intermediate, no carbocation is formed here. So in step 1 we have a carbocation here. Next, there is no partial bond formation with the carbon during the reaction. So what is this partial bond formation? So here there is a partial bond formation. Okay, this bond will break after some time, right? So we call it as a partial bond formation. Here what happens? Here a carbon forms a partial bond with the nucleophile and the leaving group. So this happens in the transition state. Okay. Next, the nucleophile attacks the carbocation from both the sides, although backside attack dominates. So here what happens now? See, when a carbocation is formed, okay, a carbocation is a planar molecule. Means what? Suppose this is their carbocation, this is like a planar molecule, and the nucleophile can attack from the top side and also from the bottom side. Okay, nucleophile can attack from the both side. So now that is what given here, nucleophile can attack from the both side. But here what happens, the attack of nucleophiles takes place only from back side. Now see, suppose this is the carbon, okay, this is the carbon and this is your leaving group, or Rx is there, right? X will leave here, so X is called as leaving group. So X is already attached to the, when the nucleophile will come, the nucleophile has to come from the back side and attack here, right? The nucleophile has to attack from the back side and this X minus will leave and we'll get Nu and R formation bond will be here now. But here it will be always from the, what I can say, from the back side, okay. Next, partially racemized products are formed. So here we will get a racemic mixture, here we will get inverted products, okay. Next, it is favored by mild nucleophile, it is favored by strong nucleophile. Now it is favored by solvents of high polarity. So solvents of high polarity will stabilize this carbocation formed, that is why we need high polarity, and it is favored by solvents of low polarity. Now rearrangement of products takes place, no possibility of rearrangement. Why there is rearrangement here? Because of the formation of carbocation. Then the reactivity follows the order. So in this one the order is 3 degree, 2 degree and 1 degree. Okay, this is very important, and here the order is 1 degree, 2 degree and 3 degree. Okay, fine. Now coming to elimination reaction. So in elimination reaction what happens? See, so this is, now we have completed haloalkanes, right, nucleophilic reactions. Now we are going towards the elimination reaction. In elimination reaction what happens? This is your alpha carbon which contains the X group, right? So this is alpha carbon, carbon adjacent to that is called as beta carbon. Now any base is there, what will this base do? They will abstract this beta hydrogen, okay, as a result of which this bond will shift here and this X will leave and we'll get a carbon-carbon double bond. There will be BH formed and X minus formed. Now this X is called as what? Leaving group. Okay. Now you can see one example here. We have taken one, this is 2-bromopentane. Okay, I hope this is visible, or I'll do it again here. 2-bromopentane. So if you see, we have 1 2 3, this is 2 bromopentane. Okay, so now this is alpha carbon, this is beta carbon, and this is beta carbon. So their beta hydrogen is here also, beta hydrogen is here also. So there can be two ways, like if the base, okay, base comes and abstracts this hydrogen and this one goes and this one will come, in that case what product we will get? In that case product we'll get is 1 2 3, and I have like this. This is the product in this mechanism. There is also one more possibility where we can have like this. Beta is there, base is there, it will abstract this hydrogen and this one will come here, okay, and this bromine goes here. Now if this mechanism is followed, then what will be the product? We will get double bond C, right? Here the double bond will form. So I'll erase this one. So here the double bond will form 1 2 3, and here the double bond is forming. So you see there are two products formed in this particular case. Now which is the major product here? So for that you should remember that the major product, okay, major product is the more substituted alkene, is the more substituted alkene. Okay, more substituted alkene. Now what is this more substituted alkene? How to find out more substituted alkene? Very easy. See, you need to make a box around this CC double bond. Okay, first one, make a box around CC double bond. Then find out how many carbons are there around this CC double bond. So if you see here, there is 1 carbon and there is 1 carbon. So I can say 2. Now if you see here, I'll make a box here. This side there is no carbon, and directly attached only you need to calculate. So here I can say that there is 1 carbon, right? So if the number of carbons attached to the double bond is more, then we call this one is more substituted. Okay, this one is more substituted, this is less substituted. And which is the major product? More substituted alkene. So in this case, which one will be the major product? This one will be the major product, right? This alkene formed will be the major product. Okay, so now if you get this, you can say pent 2-ene. So what is the name of this compound? Pent 2-ene, right? So this is 81% formed and this is a 19% formed. Okay, so how to identify major product? You have to draw a square around the CC double bond, then you have to check on both sides of the double bond how many carbons are directly attached. So here you should not count this carbon and here you should not count these carbons because it is not directly attached to the double bond, right? Okay, so I hope this is clear. So this rule, okay, this getting major product, more substituted alkene, this is given by a rule that is Saidzev rule. Okay, Saidzev rule says that during the elimination, more substituted alkene is formed. Okay, next. Okay, now the third one, that is reaction with metal. So first of all, if you take any Rx, okay, and you react with Mg, so what happens? We get this Mg get inserted, this Mg gets inserted between this CX bond. So we'll get CH3 CH2 MgBr. This is nothing but your Grignard reagent. Okay, now coming to Woods reaction, this is also a name reaction. Here if you take Rx 2Na in presence of dry ether, okay, then what will happen? This X will go and we will get NaX and RR. Okay, so the reaction you can think like this. We have Rx, okay, and we have Rx and we have Na, right? So 2Na is there. So this RR will combine and this NaX will form and this bond will break. So I'll get RR plus 2NaX. Okay, done. So now let us start solving some questions. Okay, a compound whose molecules are superimposable on their mirror images even though they contain a asymmetric carbon atom is called. Okay, so these you should know that these are the compounds called as meso compounds. Okay, so meso compounds, like for example, if I draw a structure like this, CH3 CH3 OH OH H and H. Okay, now you see this is a chiral center, this is also chiral center because the 4 groups attached here are different, right? Similarly, here also this is a chiral center because four groups attached to a carbon are different now. But you can see a plane of symmetry here. Plane of symmetry means if I cut the molecule in this place, you can see exactly this one is equal to the upper half, right? Such compounds are optically inactive, okay? So even though they have chiral compounds, even though they have chiral carbons, but still they are optically inactive due to the presence of plane of symmetry, okay? Such compounds are called as meso compound, okay? Okay, next if we draw the next question, optical isomerism is exhibited by. So for optical isomerism, what is the condition? So first of all, let us know what is the condition for optical isomerism. Condition of optical isomerism is presence of chiral carbon. Okay, now what do you mean by chiral carbon? That means all the four groups attached to carbon must be different, okay, must be different. So this is the condition for chirality, or this is the condition for optical activity. Now let us see the structure. Primary butyl chloride. So if I do option number A, butyl chloride, CH3, CH2, 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 Cl, right? Now if you see this one, in this particular carbon, okay, here there are 3 hydrogen, 2 hydrogen, 1 hydrogen. Here you see this side there is carbon, this side there is chlorine, but here both the sides it is hydrogen, right? So that is why this cannot be the answer. Now secondary butyl chloride. So if I see option number B, secondary butyl chloride, I'll get CH3, CCl, CH, CH2, CH3. Okay. Now if you see here you can see that this side there is methyl group, this side there is ethyl group, this side it is chlorine, and this side it is hydrogen. For all the four groups attached to the carbon are different. So in this case, this can be an optical isomer. Okay, so we can see this. Next, tertiary butyl chloride. So if I draw the structure of option number C, that is tertiary butyl chloride, then the structure is like this. Okay, now here you see all the 3 carbons attached to the central carbon are same. Here also methyl group, here also methyl group, and here also methyl group. So that is why this is an inactive, optically inactive. So this cannot be the answer. Now isobutyl chloride. Now see the fourth option, that is isobutyl chloride. So if I draw isobutyl, it is CH3, CH, CH3, sorry, CH2Cl, right? So here it is CH2Cl. So now what I can do, this carbon we can write it as CH3, CH, CH3, CH2, and then Cl, right? So if you see here, these 4 hydrogens, this carbon is having 2 same group, that is 2 hydrogens are present. So this also is optically inactive. The correct answer for this question will be option number B. Okay, I hope all of you can see all the options. Okay, now let's do the next question. An alkyl halide may be converted into alkene by. So if you see an alkyl halide, so CH3, CCl, H, and then I will have another CH, H, CH3, right? So in the presence of a base, what will happen? This base will take this, base will take this hydrogen. Okay, 1 second. So if the presence of a base, what can happen? This base can abstract this hydrogen, this bond can shift here, and this chlorine can move out. So we will get CH3, CH double bond, CH2. So an alkyl chloride can be converted to an alkene by which method? This method is called as beta elimination, right? We have already discussed beta elimination. The correct answer for this question will be option number C. Okay, so let us see the next question. The rate of SN2 reaction is maximum when the solvent is. Okay, so about the solvent it is asked. So if the solvent, you should remember, it should be polar and aprotic solvent. Okay, is required for SN2 reaction. So out of this is having protic, this is also protic. DMSO is a polar protic solvent. Benzene is what? Non-polar solvent. Okay, so we need polar protic solvent. Okay, correct answer is option number C. Okay, next we have lot of questions to practice, so please answer all these questions. Okay, next, which of the following statements are not true? Okay, this is very important, you should keep in mind, not true about SN2 reactions. Okay, the first one, they occur only through a single transition state. This is correct. They are favored by polar protic solvent. Just now we discussed we need polar aprotic solvent, right? So this can be the incorrect one. Next, they are favored by the solvent DMSO. Yes, because this is polar aprotic solvent, right? DMSO is a polar aprotic solvent. Next, rate of reaction depends on the concentration of the nucleophile and the alkyl halides, right? Because it is bimolecular reaction. Okay, the correct answer for this question will be option number B. Okay, next, the reaction RBr plus NaCN gives RCN plus NaBr is an example of. So here what happens, RBr, when you take NaCN, that gives you Cn minus. Okay, and here we have discussed this is Br minus and this is Br plus, R plus. So this Cn, this negative part will attack on this positive part and this part will be going out. So what I'll get, RCN. Right, so now you see what earlier it was RBr, now it became RCN, right? R is still there, this Br is replaced or substituted with Cn group. So this is called substitution reaction. Now it is substituted by what? This is a nucleophile. Why? Because it has charge. So this is substituted by a nucleophile. So we call it nucleophilic substitution reaction. Okay, answer is option number C, that is substitution. If more precise you want to go, then it is substituted by a nucleophile. So we will call it as nucleophilic substitution reaction. Okay, next, the tertiary alkyl halides are practically inert to substitution by SN2 mechanism because. So see, if you see SN2 order, what is SN2 order? Primary, secondary and then 3 degree. And what is the basic mechanism of SN2? If you see, just revise, we have Rx, okay, and then Nu comes and attacks from the backside, okay, to form a transition state, that is Nu, R and X. This is given what? Transition state, right? Now this one will give you NuRx is formed. After this bond will break and we get Nu and R. Right, this is the new compound. So now why this one? So what basically nucleophile needs? What should be the favorable condition for this nucleophile, that it can easily come and attack from the backside? So it should have less, what I can say, the the steric hindrance or the vacant space should be more, okay, or the disturbance should be less. Okay, so now that is why if you take tertiary here, so we have carbon, 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 carbon and then X, and in this case if the nucleophile has to attack from this carbon, then it has so many hindrances here, so many objections are there, so many restrictions are there, this reaction speed will become slow. So what is the major reason why tertiary halides do not undergo SN2 reaction? Because of steric hindrance. Clear? Option number D. Okay, next, which of the following is correct order of decreasing order of SN2? So again, if I write SN2 order, we can just revise it: primary, secondary and then tertiary, right? So what are the options? We have R2CHX, that means like this, R2CHX. So this is which degree, or how to know? The carbon which contains the X is attached to 2 other carbons. So this is secondary carbon, right? Next coming R3CX. So it is CXR3, right? Now this is what the carbon containing the X is attached to 3 other carbons, right? So this is called tertiary. Then we have RCH2X. We have RCHX and R. So the carbon which contains X is attached to 1 more carbon, right? So this is called as what? Primary. So according to this one, RCH2X should have maximum. So we can eliminate this option and we can eliminate this option, right? So RCH2X we got. After that secondary, that is R2CHX. So that is R2CHX. Here it is tertiary. So we can eliminate this option also. Correct answer will be option number C. Clear? Very easy question. Next, arrange the following in decreasing tendency towards SN2. Again same thing. So if you see here, CH3, CH2, 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 Cl. So if I just draw this part, how it is? CH2, okay, CH2, Cl and then C here. So this is what? This carbon which contains the chlorine group is directly attached to only 1 carbon. So this is primary, okay. Next, if you see this part, okay, CH3, so it is like this, 1, 2, then 3, 4 carbons are there, Okay, in the second carbon chlorine is there. So the carbon which contains the chlorine is attached to 2 more carbons. So this is secondary carbon. Now if you see here, CH3, this one, we have 2 CH3 attached here, then we have CH2 and then Cl, right? So here you see this carbon which contains the chlorine is also attached to only 1 more carbon. The carbon which contains the chlorine is attached to only 1 carbon. So this is also your primary carbon, right? Next, if you see this one, this structure is like this, C, C, C and then Cl. So the carbon which contains the chlorine is attached to 3 more carbons. So this is tertiary, right? So definitely what we can say, we have to tell in the decreasing order, right? So primary has to be maximum. So you can see only one option where primary is maximum. So we can easily eliminate these 2 options. Now you may think that primary is also third. So this can also be answered, but we can eliminate the last 2 options definitely because these are not primary. Now if you compare these 2, okay, the first one and the third one. So let us draw the structure in detail now. For first one it is CH3, CH2, CH2, CH2 and then Cl. And the third one, right? Yes, the third one is CH3 whole 2, that is CH3, CH3. Then we have CH, okay, and CH2Cl. Okay. Now if you see this one, see this is also primary, okay, but here when the nucleophile wants to come and attack on this carbon, there will be some abstractions from this carbon, right, because it is a very good group present over here. So whereas here if you see, here hydrogen is present, right? If I draw like this, then this one. So here if the nucleophile attacks, here it will face hindrance from hydrogen, whereas here it will face hindrance from CH3. So where the hindrance will be more, in the second case hindrance is more. Steric hindrance is more, right? And we know that SN2 reaction is inversely proportional to hindrance, right? Less is the hindrance, more is the reaction. So because here more hindrance is there, less reaction will be there. So after first 1 will come and then 3 will come, okay, but both primary will be first. After that secondary 2 and then last one is 4. So the correct answer for this question is option number A, okay. Now coming to question number 10. Elimination of HBr from 2-bromobutane results in the formation of 2-bromobutane. So if I see, so I have CH3, CH, so this one I'll do like this, will represent all the H like this. So we have CH2 and then we have again C, H, H, then we have one more H and then we have bromine group, okay. This is your 2-bromobutane, 2-bromobutane, okay. So now what happens, elimination reaction will take place. So what is this carbon which contains the functional group? This carbon which contains the functional group is your alpha carbon, the near carbon are beta, right? So now the base, what the base can do, the base can abstract this hydrogen and the base can abstract this hydrogen, right? So if I abstract this hydrogen, this bond will come here and we will get the product here as CH3, CH, double bond C, then H and then CH3. So here one H is missing, okay. So this will get one product. If this hydrogen is taken out from the base, then this one will go and this one will form. So this one will give you CH3, CH2, CH, double bond CH2, right? So these are the 2 products formed here. Now what happens? Now you need to know that if this one is formed, okay, which is a major product here. So what is the name of this compound? But 2-ene, 1, 2, 3, 4. So I can say this is but 2-ene and this is but 1-ene, right? And we have discussed that when I told you to find the major product, what you have to do, you have to make a box here, okay, and you have to see to this double bond how many carbons are attached. So here one carbon, here one carbon. So to this double bond 2 carbons are attached, and I'll make a box here, and to this double bond only 1 carbon is attached. So this is more substituted, and hence this will be the major product. Okay, which rule says this? The rule, this is given by Seidzeff rule, right? If you have remembered Seidzeff rule that we have discussed in today's class, right? So the correct answer for this question will be but2-ene. Okay, predominantly but2-ene. Okay, next. Okay, now we will go to the reactions of haloarenes. Okay, so we have done with haloalkanes reaction. What were the reactions? Let us have a quick revision now. First is nucleophilic reactions. Under that we saw so many nucleophiles are there: AgCN, KCN, H2O, OH minus. Then you have NO2, KNO2, AgNO2. Then you have LiAlH4. All these reactions are there in the nucleophilic substitution reaction. Now nucleophilic substitution reactions are of two types, SN1 and SN2. We saw their differences, and the majority that you have to remember is SN2, primary, secondary, tertiary. In SN1 it is 3 degree, 2 degree, 1 degree. Okay. Now coming to the next was elimination reaction. Here also you have to remember Seidzeff rule, the most important thing, and the last one is reaction with metal. Here we saw the reaction with sodium metal and your Wood's reaction. Okay, so that's done for that. Now coming to the the reactions of haloarenes. So haloarenes, as we have studied, has three reactions: nucleophilic, electrophilic, and reaction with metal. So we'll start with the first one, that is nucleophilic substitutions. Okay, now if you see nucleophilic substitution, the first thing that you have to remember is the haloarenes are very less reactive towards nucleophile. Haloarenes are less reactive towards nucleophile. Now what is the reason for that? The reason is, first is resonance effect. Now see, what happens when you have a haloarene like this. Okay, X is there. Okay, now I'll show the bonds here so that we can see the resonating structure. Now this X has lone pair of electrons, right? So now what happens, these lone pairs of electron come here. Okay, and this bond shift here. So I'll get a resonating structure like this. We will have a double bond, partial double bond here, and a negative charge here, and this is like this. Okay, so now what happens, now this X is tightly bounded to the benzene ring. Why? Because it is not only attached by single bond, it is attached sometimes with a double bond. So why we, due to resonance effect, what happens, there is a partial double bond character. Okay, partial double bond is formed, so it is very difficult to remove this X. Now what generally in a nucleophilic reaction will happen? See, suppose this is a benzene ring, X is there. What should happen? Nucleophile should come, attack on this one, X should leave, and we should get this one, right? Right. So this carbon X bond has to break, but what happens in case of this haloarenes, this carbon and X CX bond is very strong, so that is why it is very difficult to break that, and that is why the nucleophile cannot attack here. Okay, now why it is very strong? The first reason is it resonance effect. Due to the resonance effect, we have a partial double bond character. Okay, so now if you see the partial double bond character, first one, second one is difference in the hybridization. So now if you see normal Rx, okay, if I compare Rx, like for example CH3, CH2, Cl. Now this carbon is sp3 hybridized, right? But this carbon, okay, carbon attached in the benzene ring is sp2 hybridized. Okay, the sp2 hybrid carbon can hold the X more strongly because it is more electronegative. So this sp2 carbon and X bond is very strong. Okay, next one, instability of phenyl cation. Now see, when this happens, if you see SN1 mechanism, what happens? Rx is there, X in the first step X goes to give you R plus, right? Because in tertiary the R plus is more stable, the order of the reaction is like this. Now in case suppose this X leaves first, then what I'll get? We will get a phenyl carbocation. Okay, and sp2 carbon is there, which is electronegative, so positive charge on the electronegative atom is very unstable. So that is why, because of this instability of phenyl carbocation, so these are the three reasons because of which nucleophilic substitution reactions are very less, or you can say not found easily in haloarenes. Okay, haloarenes are less prone to nucleophilic reactions because of these factors. First is the resonance effect, second is the hybridization of the carbon, and third one is the instability of phenyl cation. Okay. Next coming to, but that does that mean that there is no nucleophilic reactions at all? So that is not correct. I told you less common or less probable, but yes, under extreme conditions the nucleophilic reactions can take place. Okay. So now if you see one example of nucleophilic reactions here, so we have taken chlorobenzene and NaOH. Okay. So OH minus is there. So what is this OH minus doing? Attacking on this carbon and this bond shifts to give you NaOH. But you see at what condition this reaction is happening? At 623 Kelvin. Okay, that means almost around 400 degrees Celsius this reaction is taking place, and at a pressure of 300 atm, which is a very high temperature and high pressure condition. Okay, now what happened? We have added one second. Okay, now suppose you have added one NO2 here. Okay, you have added two NO2s here. Okay, now what will happen? The reaction is still happening here. Again OH minus is there, OH minus is reacting here. Okay, and chlorine is leaving. So this one, but you can see the temperature has decreased to 368 Kelvin. Now if you take 3 NO2, okay, 3 NO2 if you take, and just by warming, okay, just by warming this reaction can happen. OH minus can attack here and this chlorine will go and we'll get here. Now here also there is, this is wrong, I have put it. So if you have one NO2, then at a lower temperature than, like for example, this is 600, this is 300, somewhere around 500 approximately. At this Kelvin this reaction can take place. Okay. So now what exactly is happening when you are adding more NO2 groups while the temperature is down? Temperature is down means the reaction is becoming faster. Okay, what happens when we add NO2 group? So here you have to remember that, see, we are attacking from a nucleophile, right? A nucleophile is attacking here. So what should be the condition of this reactant? The reactant should be behaving as a good electrophile. In chemistry, all organic reactions are between a nucleophile and an electrophile, right? So if this is a very good nucleophile and this is a very good electrophile, the reaction will happen faster. So now what happens? For electrophile means what? Deficient of electrons. So what is this NO2 groups doing? These are electron withdrawing groups, right? So what exactly these electron withdrawing groups are doing? They are removing electrons, right? So if they are removing electrons, the benzene ring is becoming more electron deficient, or it is becoming a good electrophile. Okay, so when we add more NO2 groups, the electrophilicity, the E plus nature of this benzene ring increases, as a result of which the reaction becomes faster. Okay, so we can note it down, very important this one. So by adding NO2 group, which is a electron withdrawing group, okay, the electrophilicity of benzene ring increases. Okay, as a result of which the reaction becomes faster. Okay, so you can note down this one. By adding electron withdrawing group, the electrophilicity of benzene ring increases. Okay, next we'll go for, so we are done with nucleophilic reactions, then we'll go for electrophilic reactions. Okay, so electrophilic reactions is what? Benzene is a nucleophile. Now electrophiles will attack on this one, right? Electrophiles will attack on this one. So now let us see this. So we have written all this reaction. So the first one is, number one is halogenation. In halogenation what happens? You take any Cl2 and FeCl3, okay, as a you can take even Br2 and FeBr3. So we can also take Br2 and FeBr3. Okay, so if I take this and if this one is reacting, what will happen? At ortho position and at para position, the substitution will take place. So chlorine will come here and come here, ortho and para position. Now a question may arise, why at ortho and para position? So now if you know that, so I can write it that X, okay, is a electron donating group, okay, and the electron density increases at ortho and para positions. right? So these are, so this means here the electron density is more and here the electron density is more. So that means these centers are more electron rich, okay, and the electrophile will attack on, because sorry, the electrophile will attack on, so this is electron deficient. Electrophiles are electron deficient. These are electron rich species, electron rich centers. So electrophiles will attack on electron rich centers and we will get products at ortho and para position. Okay. Next, for nitration, means to add NO2 group. For nitration, what we need? Concentrated HNO3 and H2SO4. So it will add NO2 at ortho position and at para position. Clear? The third reaction is sulfonation. Okay, concentrated H2SO4 and heat you have to give. This will add SO3H at the ortho position and SO3S at the para position. Okay, so this is para position and this is ortho position, right? This is ortho position, this is para position. Next, coming to Friedel-Crafts alkylation. So in this we have to take any alkyl halide with AlCl3. So this one will add CH3 at the ortho position and add CH3 at the para position. Okay. Now we can also do acylation, Friedel-Crafts acylation, CH3COCH3. So here this acyl group is added. Okay. So this one will add at the para position and at the ortho position. Okay. So 5 reactions we have, 5 electrophilic reactions of haloarenes. First one, halogenation. What is the reagent? Cl2 FeCl3. Second one, nitration. What is the reagent? Concentrated HNO3 and concentrated H2SO4. The third one, sulfonation. What is the reagent? Concentrated H2SO4 and heat. The fourth one, Friedel-Crafts alkylation. What is the reagent? CH3Cl AlCl3. The fifth one, Friedel-Crafts acylation. What is the reagent? CH3COCl AlCl3. Okay. So 5 reactions of electrophilic substitution haloarenes are done. Okay. Now this third, that is your reactions. We'll do some questions first from here. Okay. Okay. Now the replacement of chlorine of chlorobenzene to give phenol requires drastic conditions, but chlorine of 2,4-dinitrochlorobenzyl is readily replaced. This is because, so just now we discussed, when we add NO2 groups, it makes the ring more electron deficient. Okay, so NO2 makes the ring electron rich. This is wrong. It makes the ring electron deficient. NO2 withdraws electron from meta position. No, if you have seen that we have added NO2 group only at ortho and para position, right? So let us see that once again. So if you see here NO2, it is ortho position, here ortho and para, ortho and para. So NO2 group is attached at the ortho position. So because it is meta, we can eliminate this option. NO2 donates electron. No, NO2 is electron withdrawing group. NO2 withdraws the electron from ortho and para position. Okay, so this is the correct answer. Donates it. Withdraws the electron and makes the electron more makes the benzene ring electron deficient. Okay, as a result of which the OH minus nucleophile can easily attack. Okay, next question, the structure of the major product formed in the following reaction is. Okay, so we have NaCN, right? So if NaCN is present, I hope this is visible. If NaCN is present, what is the nucleophile? CH minus. So this is your X will be replacing this CN, and we have discussed that this CX bond cannot be replaced here, right? This because this bond is very strong. This bond is very strong, right? So only the alkyl RX part can be replaced easily. So here you see I is replaced, so this is wrong. Okay, here CN is added somewhere here, that is wrong. Here if you see again I is replaced, so this is wrong, but here you see only this chlorine is replaced. The correct answer for this question is option number D. So here I want you to write down a note that, in haloarenes, this X cannot be replaced by nucleophile, cannot be replaced by nucleophiles. Okay. So that is why this cannot replace this one. Anything, here anything, X means not halogen, any group, it can be anything. Okay, it can be replaced as we saw in NaOH, but under very drastic condition after adding so many electron withdrawing groups. Okay. Next, the halide which will not react with benzene in presence of anhydrous AlCl3. Okay. The halide which will not react with benzene in presence of anhydrous. So we have this one. Benzene is there and different halides are given and AlCl3 is given. Okay. Fine. So for this, what actually happens in Friedel-Crafts reaction, suppose we have this CH3Cl, okay, and we have taken AlCl3. So what happens, this AlCl3 abstracts this chlorine, okay, and we get CH3 plus and AlCl4 minus. Okay, now if benzene ring is there, okay, so in this benzene ring, this group, this lone pair of electrons attack this CH3. So first of all, what is this is generation of electrophile. So that should happen properly, generation of electrophile. Okay, so here generation of electrophile can take place, here also it can take place, but here if you see, this is C6H5Cl, right? If I take this one, so this is C6H5Cl and AlCl3. So if I take this one, so as we discussed, this bond is very strong, right? So this AlCl3 cannot take this chlorine, okay? The AlCl3 cannot take, as it can take here, but here it cannot take this Cl3, this Cl, right? Why? Because this bond is very strong. So in this case, there will be no generation of electrophile. If there is no generation of electrophile, then there is no reaction, right? The correct answer for this question will be option number C. Okay, now it's time to practice some questions, okay? So before that, we will do the test yourself question that I gave you in the last class, the homework question. The reaction of primary alcohol with which of the following will give you purely a haloalkane. So we have discussed different methods of preparation of haloalkanes from alcohols. If we revise, first is HCl, ZnCl2, NaBr, H2SO4, PCl3, PCl5, right? Then we have SOCl2, that is your sulfonyl chloride, thionyl chloride, okay? And one more was there, if you remember, we have taken HCl, ZnCl2, then we have taken NaBr, H2SO4, then we have done PX3, we have done PCl5, okay, then was X2 red phosphorus, right? X2 red phosphorus, and then we have sulfonyl thionyl chloride. So thionyl chloride, told you that is the best preferred method because the byproducts produced here are gases, right? So the correct answer for this question will be option number C. Directly we can obtain purely a haloalkane from this method, okay? Next, what is okay, so this we have already discussed in my previous class. Okay, we'll go to the PYQs now. In the following pairs of halogen compounds, which compound undergoes faster SN1 reaction? So SN1 order, remember, 3 degree, 2 degree and 1 degree. Okay, so the first one, if we see out of these two, okay, so this is a 3 degree, okay, and if you see here, this is a 2 degree. Right, so this is 2 degree here and this is 1 degree here. So this one and this one. So we can see, first we can eliminate this option. Yes, this can be there, this option can be eliminated. Now here this is correct, but this second option is wrong. Here both are correct. So the correct answer for this question will be option number D. Okay. Next, which one of the following chlorohydrocarbon readily undergo solvolysis? So see, solvolysis, hydrolysis, these all undergoes by SN1 mechanism, okay? Now when SN1 mechanism is there, the thing you have to check is the stability of carbocation. Stability of carbocation. Where the stability is more, there the reactions will be faster. Now if I see option number A, how the carbocation will form here? So we will have in option A, this is the carbocation formed, right? In option B, what will be forming? We will have this one, okay, then we have CH2 and CH2 plus, okay. Next we see option number C, that is, it is option number C. If we check, we will get CH2 double bond CH plus, okay. Now D is benzene and it is 1 plus is there, right? So now if we see here, okay, now the stability of carbocation we need to check, okay. Now if you see, this carbocation is highly stable because of resonance, right? This is which type of carbocation? Benzyl carbocation, right? This is very stable. This is stable but not as stable as this one. So if this is the highest, this is unstable, this is also unstable as the positive charge is on the sp2 carbon. So these two are definitely not the answers. Now if you compare these two, here it is stable but here it is more stable due to resonance. The correct answer for this question will be option number A. Okay. Next, coming to question number 3, the order of reactivity of the following compounds in SN2 reaction. So for SN2 reaction, what should be considered? Steric hindrance. Steric hindrance should be less. In SN1, what you should consider? Stability of carbocation. So first let us draw this structure. So first is C6H5CH2Br. So 1, 2, 3, 4 compounds are given, right? The order of reactivity of the following compounds. So we have C6H5CH2Br, C6H5CH3Br and C6H5CCH3, C6H5Br. Okay, so first let us draw all these structures. So first of all we have C6H5, so I'll draw like this. Okay, then we have CH2Br, CH2Br. This is first compound. Okay. Next one is C6H5, so we have C, then we have H, then we have Br, then we have C6H5. So sorry for the benzene ring got little distorted, but fine, we can understand that one, right? Now third one is C6H5CH3Br. So we have C6H5 CH CH3Br. Next okay, this is not option, this is the third compound and this is the fourth compound. So fourth compound is C6H5. Okay, so I'll draw the aromatic ring. So here some mistake happened and here. Okay, fine. Now if I draw here, I'll get C6H5. Okay, then we have C, then we have CH3, then we have Br, and then we have C6H5. Okay, so now you need to see where the hindrance is less. Okay, so now if you see the first compound, okay, first compound, if you see both are H here, right? So definitely this one is less hindered, right? So the first one, this compound will react faster. Okay, so this one will be fastest. So where you can see this compound at the last, okay, it is given to you in the increasing order. So here I can find this compound last. Okay, only one option. So this has to be the correct answer. We can eliminate all these options, right? But again, let us check after this what happens when there is here one only CH3 is there, right? So this can be the third one. So that is only CH3 is there. Next, if you see here there is also 2 phenyl groups, here also 2 phenyl groups, but here with phenyl group there is a CH3, here with phenyl groups this is a H. So this is less hindered now. So that the previous one will come this one and the last one will be 2 C6H5 with 1 CH3. Okay, the correct answer is option number A. Okay, now we will go for some PYQs also. So I think these are also PYQs. Okay, so yes, these all are question number 1, 2, 3. These all are PYQs. Okay, now identify the products A and B in the reaction. This is very important question. Very important question. Okay, so Rx plus AgCN, you should remember it gives you NC nucleophile, right? So we get RNC. Okay, so we can eliminate these two options. And KCN gives you CN nucleophile and RCN is formed. So this one is the correct answer. Okay, fine. Now another question here, which of the following halide shows highest reactivity towards SN1 reaction? Okay, SN1 reaction means the stability of carbocation should be more. So here I will, so on option A, what carbocation we will get? CH3 CH2 plus, right? In option B, what carbocation I will get? CH3 CH2 and CH2 plus. Now in option number C, what we will get? C6H5 plus. In option number D, what I will get? C6H5 CH2 plus. Right. So now if you see, just now we discussed this is benzyl carbocation highly stabilized due to resonance. Okay, so the correct answer for this question will be option number D. Okay, so yes, so which one is this one? Option number D. Okay, fine. So now this is a question that is a homework for you. The hydrolysis of optically active 2-bromobutane with aqueous NaOH results in the formation of? The question is hydrolysis of optically active 2-bromobutane, right? 2-bromobutane is there. So we have CH2, CH3. 2-bromobutane is there. So if we want to react it with NaOH, okay, then what will be the product formed? You have to answer. Okay, fine. So please try this question and answer this question in the comment section. So I hope today we have completed one of the most important topic of haloalkanes and haloarenes, that is the reactions, and I hope you would have revised everything. If not, we have drawn in the flowchart form. Please try doing it in the flowchart so that you can recall it very easily. Okay, so yes students, please remember we have to hit that perfect 60 score. We have to study daily, we have to work hard daily. So please be with me every day at 6 p.m. so that we can complete the syllabus well in time, practice a lot of questions and master all the concepts. Okay, so yes, now I hope you all are enjoying the classes every day. If you are liking these classes, do not forget to subscribe the channel. Okay, thank you for watching and see you in the next class of this series very soon. All the very best for your KCET 2025 preparation. Okay, remember 60 out of 60 in chemistry.